So when you think of Isaac Newton, most people probably think of the story of the apple. The apple falls, and he comes up with this law of gravity. And there may be some truth to that. I'll tell you about that in just a moment. Because basically Newton was in college in London when the plague swept through, and he was forced to go out to the farm where he grew up. And it was during that time that maybe he did, upon seeing an apple fall, start to think about gravity and the big connection he made that no one else had made before. And you can imagine him seeing an apple fall and then maybe looking up in the sky and noticing the moon out and putting those two things together, that the same force that's pulling an apple out of a tree might be the same force that's controlling the motion of the moon. Nobody had put that together. Now, when he came up with this basic theory, again, as a very young man, he didn't have the whole thing worked out yet. There's no doubt about that. But when he did have it worked out, here's what he found out. First of all, the basics. Everything with mass has gravity. That was one of his major discoveries. When you look at this equation in a moment, you'll notice it doesn't say insert mass of planet, mass of star. It just says M. You have your own gravitational field. Now, you may notice that you don't have things orbiting you right now, and there's a good reason for that. The reason we'll get to in just a moment. First, let me just mention this experiment from the 1700s. Cavendish's experiment proved Newton was correct. It actually showed that a couple lead balls actually had gravity. They attracted each other, and they could measure that. So that was a really neat experiment to confirm his idea. Another thing we know about gravity is that it's a one-trick pony. It attracts. That's all it does. Now, if you think, well, so what? What's the big deal? Well, remember, the other force of nature that you deal with every day is the electromagnetic force. And that force, as we know, like let's just deal with magnets, we know that like magnets, like sides repel and opposites attract, right? That famous saying. So electromagnetism can repel or attract. What about gravity? Well, oddly enough, it just attracts. And again, we don't really know why there's such a difference there. That's one of the fundamental things we have yet to figure out about the forces of nature. But speaking of the force of nature, the one thing that might surprise you and a lot of people is that gravity is by far the weakest force in nature. Now, if you're thinking, well, how does it dominate, let's say, the solar system? Well, the deal is, when you have something like the size of a planet or moon, they are not electrically charged objects. So they're neutral in that sense, and that way the electromagnetic force is not involved. So gravity wins sort of by default. Gravity dominates sort of by default. Of course, we know on the whole scale of the universe now, gravity is getting dominated right now by something called dark energy, and we don't know what that is yet. That's very exciting. But amongst the forces that we know and understand, gravity is by far the weakest force, which is why you don't have stuff orbiting you right now. It turns out it takes a whole lot of mass for that gravity to really be noticeable. One measure of gravity is called the gravitational constant. Newton figured this out on paper. Cavendish figured it out with his experiment. He proved it. The gravitational constant is a number, and it kind of gives you a representation of how weak gravity is. The number is 6.67 times 10 to the negative 11th. That is an incredibly small number. It's very, very close to zero. Let's take a look at the equation here. We'll watch here in the upper right as Newton makes his discovery here. Oh, he's asleep. Gets bonked on the head, and there it is. So that's kind of funny, but obviously that's not how it worked at all. When he saw the apple again, he just was getting the very rudimentary ideas of gravity at that point. Here is Cavendish's experiment with these lead balls. This is a modern version of it using a laser, but the lead balls attract, and there's a laser hitting a mirror, and as they turn, they can measure the rotation rate and see how much they're attracting, and guess what? It goes to that letter, that number I told you about, 6.67. We all refer to that as big G in physics and astronomy. It's literally just called big G, the gravitational constant. And as far as we know, that's just an episode there where Brian's showing Peter that even a person has gravity. Anyway, that number, that gravitational constant, is a really, really small number. So how does this work? Well, when you look at the equation, there's mass involved and there's distance involved, and then there's big G. Big G is a constant, so it's not going to change here or on Mars or in another galaxy. We think that's the same everywhere. So what affects gravity? Number one, you have mass. The more mass, the more gravity. This should make sense. It's common sense. If I say, hey, you're going to get to land on 2 different planets and one of them is twice as massive, you would assume that there's more gravity. And in particular, if it's twice the mass, it's twice the gravity. If it's 5 times the mass, it's 5 times the gravity. So the math is super easy. There's nothing to do. The other factor determining gravity, and this should make common sense as well, is distance. So if you're in your spaceship close to a planet and you fly farther away, guess what? Less gravity. Exactly what you'd expect. However, the distance, the math gets a little trickier because it involves something, it obeys something called the inverse square law. Here's how it works. If you fly your spaceship twice as far away, gravity is only 1/4 as much. Here's how the math works. You take the distance, whatever number, however much it changes, you do exactly what the law tells you to do. You inverse it. That means you take 1 over that number, and then you square it. Inverse it, square it. Flip it, and square it. So if I say your spaceship is twice as far away, you take 1 over 2, and then you square it. And the answer is 1/4. So gravity is only 1/4 as much. If you move your spaceship 3 times farther away, think about it for a moment. I won't say the answer just yet. If you move your spaceship 3 times farther than its previous position, what happens to the amount of gravity? 1/9. You flip it, that makes it 1/3, and then you square it, not double it, you square it, that would be 1/9. Now notice what's happening. Gravity is dropping off very quickly. It turns out that the distance has a much greater effect on gravity than the mass. Let me say that again. Distance has more of an effect than the mass. So going farther away from a planet or a moon or a star is going to decrease gravity very quickly. This inverse square law is incredibly important in nature. It's just the way that things behave. Look at this. Light behaves the same way, which will be very important when we study stars. And that's because what's happening is, whether it's gravity or whether it's light, you start out with something, and as it spreads out over a larger area, it gets less intense, it gets weaker. Think about dropping a rock in the middle of a pond. Okay, those waves are going to very quickly dissipate because it's the same amount of energy. You drop that rock, okay, the rock has potential energy, you let it go in the pond, it hits with a certain amount of energy, and that's it. Now that energy, as the waves spread out, the energy is literally spreading out over a larger area, meaning at any given point it's weaker and weaker and weaker. And as you can see from the picture, look at this. If you go 1 unit away from the light, it spreads out over a square. But if you go 2 units away, 2 distances, look at this. It's spreading out now over 4 squares. So it's only 1/4 as intense. One of my favorite analogies of this is with a spray paint can. If I take a spray paint can and put it right up here close to my computer and spray it a certain amount of paint, it'd be a really thick area of paint. But if I now take the same amount of paint, I scoot it back, spray with the spray paint can, guess what? Same amount of paint is going to spread out over a much larger area because I'm farther away. But that means that any given area is not going to be as thick, right? The paint won't be as thick. It won't be as intense. So it kind of just makes common sense that things in nature behave that way. Here are some of the problems we'll work in class. We'll get to that in class later. I want to mention a little bit about orbit while we're talking about gravity. Gravity acts as what we call a centripetal force, a force toward the center. Toward the center. Think about taking a rock on the end of a string and whirling it around and around and around. The tension in the string acts as a centripetal force. It's actually a force because you're pulling on it with your hand, and that's going to be toward the center, and it allows the rock to go in a circle. As long as you keep tension in the rope, it'll keep going in a circle. You can think of gravity as kind of like this invisible string. So let's think of the sun. It has this invisible string to the earth, and as the earth goes around and around, it keeps the earth from flying off in a straight line at constant speed. Newton's first law, right? That's what the earth wants to do at any given time. It wants to fly out into space in a straight line, but instead gravity pulls it back in and keeps it in a nearly circular orbit. So it takes a centripetal force to go into orbit. That's what's required. In this case, this invisible string that we call gravity. So that's an important concept there. We'll go over that a little more in class, I'm sure. Now, when two things orbit each other, we tend to think of space, and especially with our solar system, we tend to think of here's a planet and here's a moon, and the planet's just sitting there and the moon is going around it, which is pretty much what is happening in the case of our Earth and our moon. But in space, it wouldn't make any sense. What if you have a binary star system? You have two stars that are the same mass. It wouldn't make sense that one of them would just dominate the other. Instead, they actually go around each other like this. That's how it would work. Because what they're orbiting is not each other. They're actually orbiting a point in between that would represent their center of mass. If they're exactly the same mass, where do you think that point would be located? If they're the same, the point would be exactly in the middle. And then you can have an in-between case like Pluto and its largest moon, Charon, where Pluto is pretty dominant, but not completely dominant. Let me show you exactly what I mean here. Let's take a look. Well, let's see. I don't know if that one's going to work or not. Let's go ahead to this. Now look at this. In case number 1 here at the upper left, let's look at the upper left. This is a case that's more or less like our Earth and moon. What happens is our Earth weighs 81 times more than the moon. We totally dominate the relationship, so much so that the center of gravity of the Earth-Moon system is located, look at the upper left, located, look at that where that plus sign is, within the Earth. So it is fair to say that the moon orbits the Earth because the center of gravity is within the Earth. That's how much we dominate. Look at the case at the upper right. This is what I said would be like a binary star system where the two stars are equal in mass. They orbit a point exactly in between. And at the bottom would be kind of like Pluto and Charon, where, yeah, Pluto's, I believe it's about 6 times more massive than Charon, but it's not so dominant that the center of mass lies within Pluto. The center of mass actually lies just outside of Pluto, which is kind of interesting. So really, I believe it, some people will argue that whatever Pluto is, whether you call it a planet or a dwarf planet, that technically Charon should be called the same thing. So maybe this is a double dwarf planet system, a binary dwarf planet system, or a binary planet system if you're a Plutophile and you want Pluto to be a planet. Anyway, regardless, the center of gravity the center of mass lies outside of Pluto. So it's not really fair to say that Charon orbits Pluto. They both orbit that point in space, which is kind of cool. Finally, let's end with a famous picture from Mr. Newton's book, The Principia. Here, Newton showed he drew a sketch like this, where he showed a cannon firing a cannonball, and he saw that if you just kept firing it faster and faster along the horizon, it would keep falling further and further away from you until finally, if you could fire it fast enough, it would literally fall around the Earth. What do we call that when something's going fast enough to fall around the Earth? We call it a satellite. Newton predicted satellites in the 1600s. I mean, it's just incredible. He not only predicted them, he actually told people exactly how fast you'd have to launch a satellite. Okay, what we call orbital velocity. Turns out the magic number, 17,500 miles per hour. That's how fast. It doesn't matter what it is. It could be a satellite. It could be a baseball. That's how fast you have to throw something to get it to fall around the Earth and keep falling around. There's a pretty simple equation that he came up with to show us this right there. It depends on that big G number. Remember that really small number. The mass of whatever object you're orbiting. It could be the moon. It could be Mars. It could be the Earth. And then the R, big R, is the distance between the center of the two objects, like the center of the Earth to the center of the satellite. Then Newton took it further. He realized if you kept going faster and faster, if you launched something faster than 17,500, it's going to keep making more and more of an elliptical orbit until finally it takes off and never comes back. That is called escape velocity. And for the Earth, it's 25,000 miles per hour. You know the old saying, what goes up must come down? Not if you throw it up at 25,000 miles per hour. It's never coming back. It never comes down. And the equation, as you can see, is very similar. You just basically take the square root of 2 times the orbital velocity, and that's how something like the space station stays in orbit. It's Awesome stuff. Thanks for listening.